Thanks for the introduction. So the topic of this tutorial is computational methods for mean-field games. And because computational methods are necessarily also related to applications and modeling, I decided to divide basically the tutorial as follows. So in the first part, I'll try to explain how to basically build mean-field game models from first principles, let's say, and try to understand basically the zoo of different mean-field game models that we get. And for the second part, I'll try to dive in more into the actual numerical methods that can be used to solve mean-field games. So that's the plan, but let's see how the things go. So the three big, let's say the three whales of mean-field games are the following three theories. So game theory, optimal control, and convex optimization. This last one is a little bit of a smaller whale because this is mostly used for specific type of mean-field games that I'll be talking about. So I'll try to talk a little bit about this, all of these three ingredients, and try to understand how we can build, how mean-field game models are built and what are the methods to analyze them. And so the cornerstone, so the basic, one of the basic ideas behind mean-field games theory is the concept of Nash Equilibrium. And so this is what we're going to start with. We'll try to get a feeling for and understand for the Nash Equilibrium. And I'll try to write down a very simple mean-field game model in a very simple static case, basically with in a finite game. And then we'll see how these ideas are getting generalized to consider more complicated games, which are differential games that lead to actually mean-field games. So for a moment, we will focus on game theory and Nash Equilibrium. And let me define what is it, and let me give you the setup. So imagine we have n players that are numbered by 1, 2, etc. n. And let's say each of the players has some strategy set, which is capital SE, and it's comprised of little si's, which are the strategies of player I. Also, let's assume that each of the agents, each of the players, so I'll use agents or players interchangeably, so has a cost, which is given by ji, and it depends on the action of the player I and on the actions of or the strategies of other players. And let's use a shorthand notation for that. We'll use SI as minus I, where S minus I are all the strategies of players except player I. So this is what the other players do. Okay, so each player has its own objective, right? And then let's say each player tries to minimize the objective. So in this case, it's usually called cost because we want to minimize it. And want to understand, so Nash wanted to understand the equilibrium configuration of this game. So what are the steady states? What are the situations that are stable for this kind of games? And he came up with the following definition. So S star is a Nash equilibrium if, so let me write it down. So if, given that the actions of the other agents are frozen at the equilibrium, so they don't change, player I cannot do better than its current position. So player I cannot unilaterally improve its position when the actions of the other agents are fixed. So these are in fact called pure Nash equilibria, and these SIs are called pure strategies. There are versions of this with mixed strategies, where actually player can choose among a finite set of strategies with certain probabilities. So that's generalization, but this is good enough for us. And so you see that if we are in such a situation, then player I doesn't have incentive to change his strategy, and so this is going to be an equilibrium configuration. Okay. So let me make some remarks about this, about the Nash equilibrium. So according to this definition, what we have is that this is a non-cooperative game. In which sense? Meaning that player I, so it doesn't care about the actions, about the objective function of the other players. So what it tries to do, it tries only to minimize its own cost given the actions of the other players. So that's why this is a non-cooperative game. So there is no cooperation, so agent I doesn't interact, doesn't try to help the other agents whatsoever. And so this paper where Nash actually introduced this was, I think, announced in 1950 in the Proceedings of National Academy of Sciences, and then the paper with proofs, I think it came out in 51. Annals of Mathematics. And so this was the, so after this notion was introduced, this became, after that it became very popular, and then it earned him a Nobel Prize in economics and etc. So it proved to be a very useful concept in game theory and economic analysis. And what Nash was basically trying to do, he was trying to extend the theory of games and economic behavior by Morgenstern and von Neumann. So I think it's game theory and economic behavior, if I'm not mistaken, which was where they wanted to study, try to do mathematical analysis of equilibrium of game theory and thus economics. And so we imagine these were quite superpowers were in confrontation, etc. So the whole it was a big topic, and so many of the great mathematicians they actually worked on these kind of topics, trying to understand strategies and etc. So what von Neumann and Morgenstern did, so they tried to develop the theory of games, and one case where they could build a complete theory was the two-player game, or the min-max game. So imagine we have a function, an objective function g, x, y, and we're trying to, let's say, minimize in x and maximize in y. So one player tries to minimize the action j in x, and the other player tries to maximize it. So they analyzed mathematically this problem, and naturally the equilibrium here is just the usual saddle point, so it's very easy to write down. So So x star, y star will be a solution of this saddle point problem if, well, if you fix if you fix y star, then x is the minimizer of the problem. If you fix x star, then y star is the maximizer of the problem. And they could then give a good mathematical analysis of this problem. But then when they tried to extend this to many player games, they encountered difficulties because it was not so obvious how you should define equilibrium configurations. And actually what they were trying to do, they're trying to set up cooperative games, which are harder, in fact, to define equilibrium points. And so they had some results, but apparently they were not so general. And so what Nash was trying to understand was basically, okay, how can we generalize this? And the correct notion is actually, in the case of non-cooperative games, is the Nash equilibrium. And let me show you why it's equivalent. So we just need to put j. So given this function j, I can put j1, which is the action of the objective of the first player, as j, s1, s2, and I'll put j2, the second player, as the negative of this j. And then you can see that so s1 star, s2 star is a Nash equilibrium if, so let's write down what does it mean, the Nash equilibrium for this choice. So j s1 star so this is what it means for player 1, right? Because that's j is equal, j1 is just the action. And for player 2, it's this inequality. Okay? And you see that these two inequalities are exactly the same as the saddle point inequality. So Nash equilibrium, in fact, generalizes the saddle point problems. And often the saddle point problems are called zero-sum games. And the reason is that because if I make this choice, then the sum of j1 and j2 is equal to 0. So the objectives of the players are, they sum up to 0. That's why saddle point problems are called zero-sum games. Okay, so that's the generalization of the notion of saddle point problems. Okay, let's try to understand now the difficulties that one encounters when dealing with Nash equilibria. So first of all, mathematical analysis of Nash equilibria is very hard because this is a system of inequalities, right? And highly coupled, and also there is no relation, in a generality, there is no relation between different costs. So it's very hard to analyze mathematically. And in fact, Nash in his paper, he mentions that for complex games, mathematical analysis of equilibria becomes more complex. Another problem there that you may have encounter is non-existence of equilibria. So in fact, Nash proved that there exist mixed strategies, not pure ones in general. So let me actually write this down. So difficulties of the analysis so the problem becomes complex for general costs and large systems. Also, we may have non-existence, non-uniqueness. So it may happen that Nash equilibria are in fact non-unique, and again I mentioned there may be non-existence of solutions. Also, another problem that we may have is the following. So what was the purpose actually trying to understand all this Nash equilibria? It was that, let's say you have a system where each player has its own objective, then they start to interact with each other, will eventually the system go to Nash equilibrium. And if let's say if we know that it's going to go to Nash equilibrium, if we find that, we'll be able to predict the outcome of a game if every player acts rationally, right? So so then we can try to understand the following problem. Let's say the players start off not at the Nash equilibrium, right? And then they try to do, let's say, best response or some kind of an algorithm where they try to arrive to an equilibrium, right? So if we would know that in some general case, players will eventually, if they apply a certain algorithm, they would eventually arrive to Nash equilibrium, then that would be a fundamental notion, right? But in fact, you can construct an example of a game where no matter what algorithm you choose for the players, there is a configuration where players never arrive at a Nash equilibrium. So it was a recent, maybe 2 years or even less ago. So I think there was a group of computer scientists who came up with this model of game where Nash equilibrium is actually never reached for certain configurations. So right. Okay, so yes, so this is another difficulty. And finally, let's try to understand, okay, how can we numerically actually solve even this simple case? So we're not yet at the case of the mean field games, which are much more complicated. But let's say in a more simpler scenario, this is, let's say, we can consider the problem on a finite dimensional case. So how can we actually solve this problem? Well, what are the necessary conditions that we can get from these inequalities? So, okay, we can get the following necessary conditions, right? Si, S star, Si star, S. So the critical point, the necessary condition, Okay, it's a general system of equations, and if we do not put any structural conditions on these JIs, okay, there is no general purpose method to solve this. Of course, you can try Newton's method, which is a general purpose method, but somehow there is not much you can do if you have complicated cost functions. And so normally when people solve this type of games, they solve it for a certain class of games where you have more structure, more knowledge about the problem, more structure, and you can basically reformulate it in an equivalent but easier problem. And that's how we're going to solve actually the mean-field games in a general setting. Most of the time we'll reformulate it to a problem where it's easier to solve. Okay, so we have this, this system that is also hard to solve numerically. Let me point out one case where actually this problem will be easier to solve. So, potential games. So there is a Shapley. So there is a certain class of games considered by Shapley, which are called potential games, which puts structural conditions on this cost GIs, and it's the following. So we assume that there exists a function phi such that if we consider, let me write it down and then I'll for all i's s prime. Let me change the notation. S hat, S prime, yeah. Okay, so for all S and S hat. Okay, so what's the idea here? So let's say the actions of the other players are fixed, right? And then we consider the difference of the value of the player I at points S hat and S prime. So we're looking at the increment of the value when, let's say, the player changes its strategy from S prime to S hat, given that the other things are fixed. Let's suppose that there exists a function phi, which we'll call potential, for which this difference is exactly equal to the difference of the function phi evaluated at point S hat, S minus I, and S prime, S minus I. Is it clear, this definition? Sorry, yes. Yes, yeah. Okay, so that's the way we kind of perceive potential in physics and like elsewhere, right? It measures the difference between the objectives, and what we're saying is that there is one function that works for all players I. Okay, so is this assumption clear? Okay, so let's see what happens in this case with the Nash equilibrium. So do you agree that we can write this in an equivalent way, which is just that the difference so I'm just writing that this difference is greater or equal than 0. And now let's use the function phi and write this as a difference of the values of phi. So phi S minus I prime minus F S right? S I Yes. So we'll have that S star in a potential game is a Nash equilibrium if phi S I star S minus I star is smaller or equal than Fs okay. And let's try to understand what is this. So let me draw it in a plane. So we have this S1 star, S2 star, and this is our Nash equilibrium. And so if it's a potential game, what it says is that S star minimizes the function on this line, on this horizontal line, and also on this vertical line, okay? So in that case, we have a better structure. It's a simpler problem. And in fact, we get first order conditions, which is just that the gradient of f S star is 0. So Nash, in the case of potential games, Nash equilibria are critical points of the potential. So this is much better, right? It's way more information and way more structure. So how can we get luckier than that? Exactly. So if we're even luckier than that, and if it happens so that phi is convex, then S star is a Nash equilibrium if and only if X star is a minimizer of function phi. So if a game has a convex potential, then finding a Nash equilibrium is just finding the minimum of the potential. Okay, this is way better problem. And there are tons of very good optimization methods to solve convex problems, and most of the time they're global methods, right? You start from anywhere, you go, you solve it. So somehow, when we're dealing with this kind of games, it's always good to understand the structure of the game well, and if it's possible to come up with the potential, let's say, and then instead of looking at Nash equilibrium, we'll be looking at the minimization problem of phi. And I will show you later today that a class of mean-field games, which is called potential mean-field games, actually is such a game. So we will see, I didn't write it yet, but we will see that that system of mean-field games can be actually formulated as a convex optimization problem. And so convex optimization algorithms can be used to solve that system. Okay. So let me see. Okay, I think I have time to tell you one more interesting thing. Okay, so what are other interesting cases where we can actually tell more? So how can we analyze these systems? And so already von Neumann made the following observation, so that the hardest problems are the problems of moderate size, which means that if the number of players is too little, so zero-sum games, min-max theory, very nice theory, they did all the work, almost all the work. So when the number of players is very large, then we're thinking about like statistical physics, right? So there is some simplification when we go to the continuum limit. It's like if we're doing like optimization, if it's like on a discrete set, it's basically a search method. But when we go to find scale of continuum, then we have gradient methods, right? So going to continuum is always, almost always a helpful and good idea. And so when we have this type of games that we want to analyze, so the hardest problems are the cases where, let's say, the number of players, I don't know, let's say it's 50. I'm making up this number, but it's not very large, but it's also not very small so that we can analyze it easily. So then what we can do, what is the simplifications, or what are the conditions under which we can try to simplify the problem? And so there are two of them. So symmetry and sending the number of players to infinity, okay? Because we're expecting some kind of things similar to statistical physics happening. And let me do it, so we'll do this, of course, for the mean field games. And as yesterday morning, Wilfried was showing you the finite player game and then sending n to infinity, getting the infinite equation. Let me just show on this very little like toy example where how this can be done. So first, let's understand the symmetry. So let's assume that all players have the same cost. Also, let's assume that players are interchangeable, which means that I don't care which player did the action, a certain action, which means that this function ji is going to be permutationally invariant with respect to second variable. So it's like there is no difference if you change the names of players. So let's assume that, in fact, that gi s minus I is equal to g si okay? So I'm assuming that for all of them is the same. Also, it depends symmetrically on the rest of the players, which another way of writing that, which Wilfried already did yesterday, is saying that, okay, it just depends on the empirical measure. So I take a nice quotient with respect to permutations. So let's do this assumption. Now then the Nash equilibrium would be that Sj star Sis right? So this would be the condition for the Nash equilibrium. I just copied the expression. Now let's assume that when we increase the number of agents, so let's make an assumption that this empirical measure converges to some distribution. So let's make this assumption. Then let me write down what we get. So what we'll get is that Js star rho star so I forgot to mention that because we are considering the symmetric case, all the strategies of the agents are the same. So yeah, this inequality becomes, so Si star is, let's say, in the support of the empirical measure of all the players. And this converges to rho star, this converges to rho star. Then we get this inequality. Of course, I'm making, so I'm not saying any, these are all formal calculations. I'm not making any assumptions, but let's say we can do this under some continuity assumptions. Well, this is an elementary example of a mean field game. Okay? Because you have the generic player. So now, because the players are interchangeable, right? So what I have is that we are at an, and also I know that the actions of the other players affect player I only through the distribution of the players. And so we are at the Nash equilibrium if given that given an action of a certain agent fixed, that agent cannot do better, and the dependence on the density is given by just the distribution of the players. Okay? So was this part clear, or what?
Yes.
Okay, so yeah. So this is an elementary example of a mean field game here. And of course, what the cases that we are interested in are going to be much more complicated. But this is the basic mechanism that I wanted to show you. So you start with a cost function for agents, which is symmetric with respect to the other agents. So the agents are interchangeable. You have symmetry. And that's, you basically pass to the limit in the Nash equilibrium definition. So why do we actually care about this? And the reason is the following. So Nash equilibria in a continuum limit yield almost Nash equilibria for finite games. So if we solve the continuum problem, then we can use the strategies obtained from the continuum problem and apply them for a finite game. And what we'll get under some continuity assumptions, etc., so under some technical assumptions, we'll get that this inequality here will not be exactly satisfied, but there will be an error term here, which depends on the number of players, and it will, in good cases, it will vanish. The limit will be 0 as the number of agents grows to infinity. So this is the reason why we make this comment that when the number of players is large, it's somewhat easier because we can approximate it with the continuum problem, solve the continuum problem, and that will give us almost Nash equilibria for a finite game. And if the number of players is not so large, then we will, of course, that approximation is crude. It's not so good. And so, of course, you can study also the problem the other way around. Like, you can study the Nash equilibria in finite game and try to understand whether they converge to the continuum case. For the differential games, so for the mean field games, this side is much harder than the other way. So it's much easier to prove that the continuum problem gives you almost Nash equilibria than that all Nash equilibria converge to the continuum one. Yep.
Yeah. So in the continuum, so is this like you're working with mixed strategies now, or?
No, for now I was just saying just the pure strategies, and this is a toy example, so I'm not putting any assumptions and.
But so does this mean like the agent can be hard? So they can be with some probability in anywhere, right? So
Yes. This S is their state space, or in this case, it's also the strategy space, and they can be distributed in the strategy space. Okay, so this is the basic idea behind all of these mean field games theories. And so the next whale here is the optimal control theory. Let me give you a quick introduction to the main things that we will need. Okay, so let's assume now that we're looking to harder games. So these are not now static and simple games like I was saying. So let's suppose that we have the following optimal control problem. So let me write down the expressions, and then I'll let me use it. Okay, let's use this and then now. So let's now consider differential games. And what is a differential game? So one instance is the instance of the optimal control. So let's say we have an agent that starts at position x at time t, and it has some control, which is v, and the dynamics of the player is given by this ODE. So this is a standard setting for optimal control problem. Z dot is fzv, and the player starts at x. And capital T is the terminal time. So when player gets to terminal time t, it pays this much cost. Okay, so that's the total cost. And what we're interested in finding minimum of this cost among all controls. So controls here play the role of the strategies in the games that I was describing before. So now these GXT are like GIs that I was, JXT are the JIs that I was describing before. But now I have just one player, so I'm starting with just one player. There is no mean field yet, just the simple case. And what we're trying to do, we're trying to understand how to solve this problem. And, the well-known optimal control theory tells us how to do that, right? So, so what we need to do is the following. We need to construct so this L is called Lagrangian, and we construct the Hamiltonian. So in the following way. And let's denote here the value of this problem. So phi xt, let's say, is the value of this problem. So it turns out that this value function is kind of like the master function of this optimal control theory, in a sense that it has all the information that we need to find the optimal trajectories. And how does it do that? So first of all, it solves the Hamilton-Jacobi equation. With a terminal condition g of x, where h is defined according to that formula. And if we have this function phi, so once we solve this equation, let's say we could solve it in some way, the way to find the optimal v is according to Pontryagin maximum principle, which is so v star So we put gradient phi instead of the variable p and solve this problem. Okay? Actually, let me write it in a more expanded way so that once we solve the Hamilton-Jacobi equation, then to find the optimal actions, we need to solve this maximization problem, which is called Pontryagin maximum principle. And again, I'm not giving here the technical assumptions that are necessary to do all this, but it's possible to do actually in quite general cases, and I'll give you three books actually where this is done in detail. So Fleming-Sonner, I think it's called Controlled Markov Processes. I think there is Bardi. I don't remember the name of this book. Viscosity Solutions and Optimal Control Theory, something like that. Theory and yes, and also in Evans' PDE book there is also Evans. There are sections to deal with it. So the technical assumptions have to be made and etc. But this is the general framework. So HJB and the Pontryagin maximum principle. And yeah. Okay. So of course, this HJB equation is a first-order equation. Therefore, in general, it doesn't have a smooth solution. So we like regularity here. And the way we need to, the notion of the solution is non-trivial here. And it's important later also for the mean-field games. And the notion of the solution that we're consider here is the notion of viscosity solutions. So here, phi in a sense of there are a number of ways to define viscosity solutions. So, or using the maximum principle, or would be just to add a diffusion term here with epsilon and send epsilon to 0. So this is the celebrated Crandall, Lyons, Evans theory of viscosity solutions. Okay, so I want to make the following comment here. So if this Pontryagin maximum principle is easy to solve somehow when we get explicit solutions depending on grad phi, then this is a nice case because so if say some function let's say it's possible, and I'll show you a case where it's possible to do. So then this is a very nice setting because we know the optimal actions in a feedback form, which means that if we are at position x at time t, then to see where we move, we just have to read from the value function. We calculate the gradient and apply whatever form we get there. And let me give you one case where this is simple to do. So let's say the control is just the velocity, fx is equal to v, and let's write down what, actually let's see what is the Hamiltonian here. So we'll have that is equal to so modulo the sign here. This is the Legendre transform that Wilfried told in the beginning of the lecture. So this minus appears because we're in the control setting, so we're looking at the backward problem. So not to have an annoying minus sign there, we just put it here. But the theory of convex conjugate, Legendre transform, and etc. works perfectly fine here. We just need to be careful with the sign. And under convexity assumptions of the Lagrangian in V variable, we can actually flip this formula. So we also have so this is the beautiful duality that you have among convex functions, that basically you can go back and forth with this Legendre transform. And let's see what is the relation between optimal pairs. By optimal pairs, I mean that what is the V optimal V corresponding to P and vice versa. And for that, so if we differentiate this first equation with respect to V, we'll get that P is equal to minus dV LXV. So, and if we differentiate this expression in P, we'll get that this is equivalent to okay. So this is the relation between the optimal dual variables, which is fundamental for us. And we are going to be using later this specific one. And so in this case, what we'll have is that V star xt is given by minus so this is the feedback form. Okay. So in case f of xv is just v, and under some convexity assumptions on the Lagrangian and smoothness assumptions, if we solve the Hamilton-Jacobi equation, then the optimal actions are given by this formula that we will need later. Do you have some questions or comments here?
It's amazing. The method of characteristics comes out of this stuff. Hamilton-Jacobi equation.
Right. Yes. Yeah.
The whole thing is incredible.
So I think we have all the ingredients to actually build up the mean field game models and consider different cases and setups. And then later we'll try to solve these problems. Okay, so we did the game theory, the optimal control, and convex optimization will come later. So yes, let me do the following. X okay, so now I'll describe the mean field game models that we're looking at. So, which is one of the main topics of this semester. So what do we have? So remember before when I was describing this Nash Equilibrium game and then going to the limit, here imagine that now we have a continuum of players. So unlike Wilfried, I'm not going from the finite player game to the continuum. I'm just working on the level of continuum. So I've already assumed that there are players that are distributed in RD, for instance, according to some measure rho. So let's say xt or rho t is the distribution of players in RD. And let's assume that for a moment that I know this distribution of the players for all times t from 0 to capital T. So instead of one agent, now we have a bunch of agents and they're moving around in the space. And let's say for a moment that I know their distribution. Basically, this rho is a probability measure on RD. And let me define the cost function of a single agent, as I was defining the cost function before. And it's as follows. So it's an integral. So it's a similar cost that we had for the single pair of optimal control. But there is a key difference. The Lagrangian here and the terminal cost here, they depend on the distribution of the players. So this is reminiscent of the, do I have it there yet? No, I don't have it.
Is that gamma of t?
What?
Is that z of t for g?
Yes, thank you. Actually, so we have to, before it was x or, so it should be, yeah. So here, yes. Yes, the final position, yeah, thank you. Okay, so that's the only change that we make into this setup, and this is similar to the structure that I had before, where Ji depended on the actions of the player and on the distribution of the rest of the players. Okay, so so we have this differential game. Each agent plays against all others, and we want to understand the equilibrium configurations of this game. And as a basic equilibrium notion, we take the notion of Nash equilibrium. Okay, so we want to understand the Nash equilibrium in this game. So, and we'll do it as follows. So let's say all agents have some forecast about the distribution rho. So they have some idea of how this measure will change. Then, according to our definition of the Nash equilibrium, optimal strategies of agents will be given as follows. So V. So let me actually here also explicitly show that this depends on rho. So the optimal actions so V is a Nash equilibrium. So the strategy of player V is a Nash equilibrium if it cannot do better unilaterally, which means that if I change V by V hat, then it's worse off. Okay? So in fact, here I'm being a little bit inaccurate. What is the inaccuracy here? So if I would write truly what is the Nash equilibrium, how should I write there? Yes, so in general, right, if we have, let's say we have finitely many players, right, and then let's say each of them has their trajectory, and then at each slice of time I'm just reading off what is the distribution. So, and then let's say I'm isolating this one player, and let's say it has this strategy, which I'm claiming is the optimal one. Now let's say I'm, so this is V, right? And let's say I'm choosing another, trajectory V hat, and I'm comparing. In general, what happens is that the distribution of the agents changes, right? Because the agent here, it's not here now, it's in a different position. So if one agent changes its actions, it alters also the distribution of the population. But the assumption that we make in mean-field games is that the agents are small and their actions, the unilateral actions, do not alter the distribution. That's why, strictly speaking, I should have written here a different row, which would correspond to these new actions V hat, but because it's a small player, this is not going to be changed. Okay? And this is the assumption of being a small player. So in all the mean-field game literature, it always starts, so assume that we have identical continuum of identical small agents, and the small means exactly that I can leave rho there. Okay?
So it should be rho hat. But
Yes, it should be rho. So if you're writing this in the finite players case, you need to write here rho hat, which corresponds to that one agent changing its strategy. Because here it's like, so this yellow is the player that we want to write the Nash Equilibrium. Let's say these white ones are rho, and rho, of course, takes into account also the position of this one agent, right? So if I change the position of this agent, of course, the distribution will change. But if we are in a continuum limit, this is not going to be the case. I mean, that's an assumption, actually, yeah.
So in the finite case, each agent has its own V as well, right?
Yes.
So if it changes its own V, it will not change the other agent's V.
No. But here, rho is the distribution of positions, right? So strictly speaking, so rho is 1 over n. Let's say we are in the finite dimensional case. Sum delta zi xi 0 t. So we have that rho is supported on the trajectories of players, right? So if I change the control for one of the players, this will change its trajectory, and so it will change the distribution.
But if you had n minus 1, it wouldn't change it, right? But which would be the actual...
If it would be n minus 1, it wouldn't change, but then the cost would not be the same. I had to change for...
so it's not in the same setup that you have this J over here with the S star.
It's the same kind of setup. So the thing is that, in fact...
Because before you had the density, I think that's what he said, you had the density of all other guys.
Yeah. So the assumption of being a small player means that you can you can write the other one or the other one, doesn't matter, in the limit, yeah. So somehow this 1 over n is the weight, and then it goes to 0 in the limit. Okay, so we have this Nash equilibrium condition, and let's see what does it give us. And from now on, I will assume that the dynamics is given by, so f of xv is just equals to v. So this is the case that I'm going to be looking. Okay, so since rho is fixed, then this rho enters just as a parameter in the Lagrangian, right? And I can write the Hamilton-Jacobi equation. So it's fixed, and so this means that V is the optimal control of this problem. And so if I denote, let's do this. So phi of xt is just the infimum j d rho. Then I have the following Hamilton-Jacobi equation. Grad phi rho is 0, h bar, where, and phi of xt is g of x, and I have the following h hat x xp rho okay, so the only thing that changes is that now I have this rho, the density of the players as a parameter, but I define the Hamiltonian in exactly the same way, and again, rho here enters as a parameter. Okay, because, yeah? Yes, thank you. Yes, exactly. Yes, this is important, actually. Yeah. Okay, so we have this Hamilton-Jacobi equation because rho is fixed. Now, let's try to understand what are the optimal actions, V star. And so from Pontryagin maximum principle that I have there, V star xt is equal to minus dph and rho again is there as a parameter, h bar. So I'm just applying the theory before, because once rho is fixed, then this is just a simple optimal control problem.
So either once rho is fixed, but this V somehow is the best V. So there's, I mean, when you write rho there, does it depend on all the other information in the problem?
At this point, no. So later,
Rho is just, you're assuming that you just
yes, yes. So agents.
It happens to be the one that works for the best.
So the way it works is like this. So let's assume so we're looking at Nash Equilibrium, right? Which means that the actions of the other agents are fixed, right?
I see. Okay, so once you have that, then it reduces to.
Yeah.
So it's not a full optimization.
Yes, because once the actions of the other agents are fixed, and the actions of one agent doesn't change, this means that this rho is fixed to be like
So
the yeah, yes, yes. So yeah, and we will need this formula. Okay, so now let's say all agents, they start to act according to these optimal policies or optimal controls. Then the dynamics of the agents will be given according to the following formula, right? So it's V star, because I assumed that F is just V now. So a generic agent's trajectory will be given by this formula, or if I replace it, it's going to be H bar X T. Let's do this. So I'm not writing xt just to save space, but so these are going to be the trajectories of a generic agent. And if we know that agents act according to this equation, the measure, their distribution will change. The equation for their distribution will be the continuity equation, which is minus divergence dph 0, and let's say they have some initial distribution, rho 0 x. And I put rho hat on purpose because a priori we don't know whether rho hat agrees with rho, right? So the mean field game case corresponds to the equilibrium where, so let me maybe, okay, here, I'll write it here. So MFG is that their actual actions, optimal actions, generate a trajectory, generate measures that coincide with their their forecast of the measure. Okay. Oh, sorry, I keep forgetting the yes. No, it's just at time t. Yes. Yes. The divergence. Oh, yes, yeah. Rho t. Yeah. And now let me summarize, so let me write down all the equations that we got. So first the HJB. Equals 0. Then I get the continuity equation and I use the fact that rho hat is rho, so we're at the equilibrium. Okay. Use one notation for. And I have the terminal data and initial condition.
You wrote the hat for emphasis over here.
What? Yeah, I wrote the hat for emphasis because this is like
I always had this in mind.
Yes. I just wanted to show that this corresponds to the equilibrium configuration. So, yeah. So if the forecast of the agents is wrong, is not at the equilibrium, then this will get corrected, right? So we'll do our actions and we'll see, okay, this isn't like rho has changed if we act optimally, and we'll reevaluate our trajectory, reevaluate, and hopefully at some point it will be in equilibrium position. So this is the typical mean field game system that is considered in the literature. Of course, the first order case where there is no noise. And in case we have a noise, so individual noise.
You got H and H bar.
H bar. Yes, because I did it for a reason. I will, yeah. And so, yes. So what I'll try to show on for the second part are some of the numerical methods to actually solve this type of problems. And I just want to make one last comment. So what I tried to do was to show how basically to build a mean field game model from basically first principles, and that amounts to several choices that you have to do. first you need to understand what is the cost for individual agents, and you can choose this Lagrangian, or you can choose reachability problems, for instance, that Claire was talking about. You can choose minimal exit time and etc. So you choose your favorite control problem, and then you put it in a mean-field game framework by adding the dependence on the distribution of players. And we will discuss different ways to do that. Yeah. So.
What's the history of all this in my telling?
Yeah. So there are two groups of people. Yeah. So Lasry and Lyons on one hand, on the Peter Keynes, Mini Huang and Roland Malhamé in the engineering community. So the difference was so the idea, the underlying structure is the same, but the type of costs that they were considering is different. So PDE people, they like to work in this setting because in that case, in many cases, you can calculate the Hamiltonian explicitly. You can work with the Hamilton-Jacobi equation directly. But control and in control and engineering, actually, this is not so. I mean, it's useful, but it's not so useful control. And so, but then in some cases, this Hamiltonian is impossible to calculate analytically. That's why. So I think in the case of Peter Keynes and others, unless it was linear quadratic, the setup that they considered was impossible to analytically calculate. But the ideas were, yeah, similar, same. Okay, yeah. Okay.